Okay. Okay, so welcome everyone for this session on modeling and simulation of solar energy systems. I think morning session there was discussion on the concepts related to solar energy systems. So this in this session we will focus mainly on solar PV systems actually. So because as you might have discussed in the morning session, there is the other alternative pathway of solar thermal as well. But here we'll be talking mainly about solar PV, and in that too also, I mean, this is actually long. I mean, a lot of things are there to discuss in this, but let's see, because my idea was of having some hands-on discussion and also demonstrating what we are doing in the PV software. So let's see how far we can go, and accordingly we'll adjust this. So to begin this thing, when we talk about PV systems, there are two type of PV systems specifically, as all of us might be aware. One are the standalone PV systems, which they are like isolated systems which are working on their own, and usually they have their own small storage, like in the form of a battery. And the other one is the grid connected PV systems, where they also may or may not come with storage depending upon the size and all. But the thing is that they are connected with the grid. So in case there is extra generation of energy from the solar PV system, that can be pumped into the grid. So we will look at first the standalone PV system and how to model it in the software PVsyst. So I'll be discussing this concepts along with their application in the PVsyst software and how this simulation can be conducted in this particular software. And if time permits, we'll be looking at few aspects of grid connected systems also, and what are the changes from the standalone system which need to be incorporated. So as we understand, as the name indicates, standalone system. So if a PV system has to run in a standalone mode, definitely it has to come with a battery storage. Because as you understand that PV, the solar radiation is intermittent in nature, and depending upon the weather profile and the time of the year and the location we are talking about, this intermittency can be of different magnitudes. So sometimes when you have the part of the year when it is the clear sky time and cloudless weather, then more or less there is a stable solar PV generation, and there is a particular trend. And obviously, as we understand, from morning to afternoon, it will peak due to the the sun's radiations peaking, and then from afternoon to evening again it will taper down gradually. But apart from that parabolic type profile over the day, the fluctuation or intermittency will be low when you have cloudless weather. But in the monsoon season, or when there is a lot of cloud cover or some other aerosol particles, then as we understand that then as the sun moves across the sky globe, there will be a lot of fluctuations which will come into picture. So in either case, we will require some backup battery storage to come along with the PV system, especially when we are talking in the standalone mode, because all our power appliances, they require a stable voltage and a stable frequency to operate at. If it's an AC system, and if it's a DC system, then only the voltage should be standard, as should be constant. So either way, the battery becomes very imperative for having along with this standalone system. So the PV array charges the battery directly or directly delivers its power to the user. Both the options can be there. And the user's needs or consumption should be well defined with its daily profile, that is in hourly values. So we'll look at it, how to define that in the software. The simulation performs a balance between the PV production, which depends on the irradiation, and the user's need on an hourly basis. So when we talk about this in the PVsyst software, if I want to do the sizing and modeling of the standalone PV system, basically what is happening is that the software is performing a simulation to balance the PV generation and the user's need in terms of the energy demand. So, and whatever is the difference, it will be managed by the battery. So if there is an excess generation, that will be stored in the battery. If the solar generation is low and the demand is high, then there will be a negative power flow from the battery. That means the battery will be getting discharged. And this energy balance of maintaining the balance between the generation and the demand and accordingly bringing in the storage into picture. This entire thing is controlled by the controller. So this controller handles the energy flow, and especially with respect to the battery. So a few things need to be taken care of. When the battery is full, the PV array should be disconnected, no, because we don't want to overheat the battery and damage it. And when the battery is empty, or it's near its maximum depth of discharge value, then the user should be disconnected, because if we don't want the battery to discharge below a particular level as well. So that all thing is handled by the controller. And in case there is a backup generator which is they are present along with this main PV system, then the controller might also manage the starting and the operation of the backup generator. So this entire thing we can look at it with this schematic diagram. Now there are in the standalone PV system also, we will discuss about these three different types or three different sizes of PV systems. So this block diagram here shows you the small standalone PV system, and this smaller systems are very simple in nature. The idea is that they are of a very low power rating, typically of 50 to 200 watt peak. So it's like a small solar home system sort of thing for maybe running a few lighting or fan loads and all. So this one is a very simple one, and here as you can see there is a simple controller which is controlling the charging and discharging of the battery. And there are these two switches as you can see in this within this controller. So as it was discussed, that if the battery is nearing its depth of discharge and there is no more charge in the battery, then the user needs to disconnect it. Or on the other hand, if the battery is getting full and there is no withdrawal from the user side, then the PV needs to be disconnected. So accordingly, those two switches are shown here. So this is the simplest one, the small standalone PV system. And as I said, this concerns very small systems, typically 50 to 200 watt peak, which have a very limited consumption, like typically some lights, radio, TV, computer, etc. Even a fridge it doesn't support. So these are like these are also being marketed these days for maybe for rural or small household applications, and by the name of solar home systems or SHS. And so with these simple systems, the PV array is usually connected directly to the battery without power conditioning. So most of these loads are DC loads only. And this implies that the PV modules should be either 12 volt or 24 volt modules, depending upon which type of system design one has adopted. So this type of installation is managed with simple controllers acting either by disconnecting the battery or short circuiting the PV modules when the battery is full. So as you can see, the controller is a simple controller. It's not an MPPT controller. Only thing it is doing is that it is managing whether the battery should be discharging or charging, whether it should be charging or not, whether it should be discharging or not. So both the sides there is the control, whether you need to connect the user or disconnect the user, whether you want to connect the battery, the PV to the battery, or you want to disconnect it. So that type of simple controller is sufficient for this small standalone PV systems. And these controllers have always the ability of controlling the load when the battery is empty. So that load control is also inbuilt there. So this is the simplest and the smallest one. Then little more advanced one with having more capabilities is this medium-sized standalone PV system. And in this medium-sized standalone PV system, as we see now, the controller is coming with an MPPT converter. So now the battery voltage and the PV array voltage will not be coupled to each other. They can be decoupled, and this MPPT converter can take care of that. So even when the IV characteristic of the PV array is changing, the MPPT converter can make sure that your battery is getting charged at the constant voltage itself. And also there is this, if you have an optional backup generator, then that can also be controlled through the same controller, and depending upon, as it can sense, it has the demand, user demand also is available here, and how much is the PV generation and what is the battery charging or discharging level. Accordingly, it can give a signal to the optional backup generator to be switched on or switched off. So these systems are medium-sized systems, and the rating here is usually in the range of 200 watt peak to 2 kilowatt peak. and these can be used for small household or communication applications. So as we saw here, the controller will include power conditioning unit and also able to perform the MPPT function for the PV array. So that means that PV array voltage is no longer related to the battery pack voltage. And also the controller can be able to control the load control, which was there in the smaller system also. So and then the energy may be used as either DC energy or fed as AC energy through an inverter. In this block diagram here, the inverter is not shown separately, but in case your loads are AC loads, then you will need to have an inverter also here, so as to accordingly feed the AC power to the respective loads. So this is the medium-sized system, and these installations may power more. It has, as the name also indicates, the power rating is higher. So this can be used for powering small households with all these different gadgets like fridges, washing machines, dishwashers, etc., or even some small electro tools and all. So this may also be used in small remote communication stations. For those applications also, this is good. And in case there is a backup, as we said, the starting and stopping of the backup, if it is automated, then that should also be controlled by the controller. So this is the medium-sized one. And then finally we come to the high-power standalone PV system. So this is like the full-fledged standalone PV system, and having all the capabilities and able to deliver higher power output also, suitable for maybe even industrial applications also. I mean, small scale industry and all. So here, as you can see, now the thing is a little more complicated, and the controller here has been split into two different parts. So there is one charge controller, or basically which is commonly known as the solar charger. And this has got MPPT ability, maximum power point tracking for the PV array. And then it also, so that particular interfacing of PV with the battery, that is being controlled by this solar charger or the charge controller along with the MPPT functionality. And the discharging part here is usually coupled with the inverter. So because this is at the high power level in terms of the household applications or small scale industry applications. So usually the loads here will be AC loads, and so definitely inverter here becomes imperative. And this inverter has its inbuilt controller for discharge control of the battery in accordance with the user loads. So now the controlling function has been split into two different controllers here. And again, the backup generator and all, if it is available, then that is also being controlled by the discharge control mechanism, which is inbuilt with the inverter usually. So these systems typically the power range is from 2 kilowatt peak minimum to maybe several dozens of kilowatt peaks, so up to 20, 30, 40 sort of kilowatt peaks it can go up. And so these installations generally use one or several solar chargers equipped with MPPT converters and DC to AC battery inverters. As I said, the controlling function, as you saw in the block diagram, that it is not a single device anymore. The controller has been split into two different parts. One is the charger, the solar charger or the charging controller, which interfaces the PV and the battery. And then there is the discharge controller, which is usually the control function of a discharge controller is usually coupled with the inverter, and that forms the interface between the loads and the battery. And also if there is a backup generator, that is also managed by the inverter. So this type of thing is like the full-fledged standalone PV system. So these are the different categories of standalone PV systems. Depending upon the application and the power rating, accordingly the suitable configuration can be adopted. So now let's, with this some basic discussion, now let's go ahead and look at how to model this system in the PVsyst software. So PVsyst is a very well recognized and good software for doing the simulation of PV systems. And this is available. You can download it through its website or PVsyst software website. And the thing is that there is a trial version which is available for free of cost for 30 days. But if one wants to continue the use beyond the trial period, then you need to purchase a license for this. So right now I'm having the trial version for this. I'll just show you the interface and how it looks like and some of the functionalities. So I'll just share my screen. So the latest version of PVSYST, which is available on its website, is PVSYST 7.1.2, and I've installed this just today itself. So this is a trial version only, and it has a validity of 30 days. So here, this trial version actually comes with all the functionalities, but only available for 30 days. That is the constraint, and one can purchase the full-fledged one if needed for a longer time. So as you can see, the when you open PVSYST, you get this type of an interface, and there are different options which are given here. So this interface is for project design and simulation. If you want to do just preliminary design, then there is a different menu for that. But that preliminary design is very crude in nature or very basic. So that's, I mean, not really recommended for us. And maybe for some small project, some school project or something, people might do those type of things. So for full-fledged system design, we go to this project design and simulation, and here there are different options. So what type of system you want to design, whether it is a grid connected system or standalone or a solar PV pumping system, that can be chosen here. So let's first look at the standalone system, and we select this standalone button. So we get this type of an interface. Now here there are a few things you need to select. The you can put some project name here, whatever you want to put, you can accordingly change this one. And the important thing is that you need to select the location, and there are different locations which are available in the database of PVSYST, and you can look it up here. So view site details, and this here has, by default, it has got Pune as the location. So you can see here the by default it is coming with this Pune as the location, but you can always choose it. If you want to choose a different location, you can go to this show map functionality, and on the map also you can select which location you want to select for your simulation. So you can zoom out, and accordingly you can select some particular location. Let's say, suppose we want to select Delhi as the location. So again, I mean, in Delhi also there'll be, I mean, this has got a high the spatial resolution of the data is good, and for every few kilometers there are data points which are available. So for different localities of a city also the data is available. So suppose I choose this location here. So this is Connaught Place in Delhi. As you can see in the right panel here, the name of the locality and the latitude, longitude, altitude, and these other things come up. So suppose I choose this one, and I accept the selected point, and I get this one. So Delhi Connaught Place has been selected here, and accordingly the geographical data has been imported with success from the map. So there is a geographical data which is available here, and there are different options. There are different databases which are available in PVSYST, and by default, as you can see, it is taking from the Meteonorm database, which is maintained by NASA. So as it says here, you can, I mean, if it is not available, then you need to import the monthly Meteo file. In case it is available, then it will be there by default. But it seems here that there is some issue. This thing is not available. The Meteo file for this is missing here. So what we can do is that we can probably we can import it from the one of these. There are 4 different databases which are available, and in this case, it's not really showing us with this availability of the data here. So what we can do is that, okay, like just to demonstrate here, maybe let me just select a different location. So I guess this one is it's having some issue with the data availability. I mean, let me just try and select a different location and see if it can give the data for this. So this one here, I mean, I guess there is some issue. We can add a new location also here, and but there is some issue with the data availability. Maybe this is the latest version 7.1.2, so they might not have maybe updated the Meteor files and all. So because with the older versions, this type of issue did used to come, and yeah, here, so maybe we can look it up here and just decide upon this. So let me just try it out here. So let's say I select this one, and so what we can do here, suppose I've selected this Paharganj locality in Delhi, and now as you can see here, it shows the available databases. There are 4 databases which can be used for this. So one is the Meteonorm database, another is maintained by NASA, the third one is PVGIS, typical meteorological year database, and fourth one is the NREL, or the National Renewable Energy Laboratory database from US. So out of these 4, only 3 are available in this case. Suppose I import the Meteonorm database, and let's hope that it gets imported so that we can move ahead with this thing. So this thing runs at the back end, and we don't need to do it manually. It, as you can see, it is linked already with one of these databases. So now it has got the Meteonorm, which is a software which makes the meteorological data available from across different locations on the globe. So it has imported the data from there. Now I can press OK, and so as you can see here, it will ask me to save the geographical site file, and it by default there's a naming pattern, the name of the location Paharganj, and the Meteonorm database. It is MN indicates that the data is coming from Meteonorm, and 7.3 Meteonorm 7.3 is the latest version of Meteonorm, so that's why MN73, and the data available is from 1981 to 1990. So let's say I save this one and I move ahead with this. So this thing is saved now, and save the early. It will generate a synthetic Meteor file containing all the meteorological data. You can also save this one. So as you can see now, this has got the, now I have got the location in Delhi. I've taken Paharganj as the location, and I've got the meteorological data from the Meteonorm database. And all the messages, if there is a prompt, then that will show up in the software here. And the color of the prompt indicates what type of prompt it is. So like this one is in orange color. The site has been modified. Please save the project. So orange color, this prompt is more like a reminder or like a warning thing. So it's always advisable to follow that. But if you don't do that, it's not that you cannot move ahead. You can still move ahead, but it's always advisable that you can do that thing. You can follow that one, whatever is the recommendation. So as you can save it with any file name. Suppose I'm saving it here as Delhi sample project. Okay, so now you can see. So now if you see, I saved it. Now there is a new prompt command here. It says the orientation is not defined, and this is defined. This is, as you can see, the color of the prompt is in red. So if there is something which is being prompted in red, that means you cannot bypass that particular comment. You have to fulfill that requirement. Only then you can move ahead. So now it says that you need to define the orientation, which is an important thing for doing the simulation on this system, on the PV system in the PVSys software. Now, what is this orientation? Let's first look at some concept related to this, and then we'll go to this thing in the software. So let me just go to the. Okay, so let's go to the slideshow mode. So as you see, we started with this one, the standalone PV system mode, and we have done all this one. So the first part, we have defined the site and the meteorological input of the project. And once we have done this, what we are now going to do is this. You will notice that in the beginning, there are two buttons marked in red, orientation and users needs. The red color means that this variant of the project is not yet ready for simulation. Additional input is required. So few things which we need to define for doing this simulation are given here. Basic parameters that need to be defined for any of the variants and not yet specified are the orientation of solar panels. So orientation of solar panel is something very critical which needs to be defined. Second is the user's needs. Third is the type and number of PV modules. And fourth is the type and number of batteries that will be used. So all this we need to define before we can run the simulation. So first thing is the orientation. Now orientation, I'll just go to this in the software, but we're just discussing this here in the concept wise. So when you click on orientation, this type of interface you will get. And here you can choose which type of PV configuration orientation you want to choose, whether you want to have fixed tilt panels, whether you want to have tracking panels. If you want to have a fixed tilt, then what should be the tilt angle? What should be the azimuth angle? And there is an optimization help also, whether you want to optimize the output with respect to the yearly output or the summer output or winter output. All those things, those functionalities are available. So this orientation tool is aimed at showing the best suited orientation for a PV system, or in other words, what you lose when not optimally oriented. Because if you don't have the optimal orientation of the PV system, then definitely you'll be losing out on some possible energy which you could have trapped and generated. So here, and then there are a few more terms which are defined. The transposition factor is a term which you'll see in the orientation dialog box. And this is the transposition factor is the ratio of incident radiation on the plane to the horizontal radiation. So because you'll notice that we usually have the tilted PV panels, and the angle of tilt, there is a thumb rule is that if you want to maximize the year round energy output, then you should put the tilt angle same as the latitude of the place. But if suppose someone wants to have different, someone has a different optimization goal, they don't want to optimize the year round energy output, rather they want to optimize or maximize some of the seasonal output. Suppose I want to maximize the winter output, then because I'm in the northern hemisphere, I'll need to have the tilt angle of the PV panel greater than the latitude of the location. Suppose I want to, someone wants to maximize the summer output, the summer season output, then they'll need to have the orientation angle or the tilt angle lesser than the latitude of the place. So accordingly, that choice can be made. So that thing has been provided here with some help also. The optimization, you can choose which type of optimization you want to have, whether you want to have yearly optimization or summer or winter. These three options by default they provide. So accordingly, you can choose that particular thing. So now let's look at this one in the software. So as you can see here in the software, it is saying the orientation is not defined. So in this bottom left, as you can see, there are these main parameters which you need to define. So first is the orientation, second is the user's needs. So first of all, let's go to this orientation. Now, when you click on orientation, as we said, you get this type of interface. And here, first of all, you can choose the field type, what type of PV panel field you want to have. So, you can have a fixed tilt panel, which is like the default, which comes here. But then there are other options also available, like you can have seasonal tilt adjustment. So if you take seasonal tilt adjustment, then you can define which particular season, what particular tilt you want to have. Then you can have single axis tracking planes. So, you can have a tracking plane. So, it will track the sun, but only in one axis. So basically from east to west usually. So then this tracking parameters and all you can define, but these things are usually not very popular these days. Why we usually go for fixed tilt panels? Because now the panel cost is very low, and so it doesn't really, the economics of having a tracking mechanism doesn't really work out in favor of the PV output. And also because when you have this tracking mechanism, the maintenance cost and other things will go up. So not really economically viable because of the low cost of the PV panels. And then also, but the options are there in the software. There is also this 2-axis tracking planes. So, you can have double axis tracking. So from east to west over the day, and then across the seasons from north to south. So those type of options are also available, but the experience says that these days what mostly people go for is the fixed orientation planes. So let's take that as the option here, fixed tilted plane. And now you can adjust the tilt angle. So the tilt angle of the place you can increase or decrease here accordingly. It can be set. The azimuth angle also you can change. So in this software, the default is facing south because we are in the northern hemisphere. So 0 degree azimuth corresponds to south facing. The convention can be different. Sometimes people have the convention as 0 degree being north facing and 180 degrees as south facing. That type of convention is also followed by many books and other literature. But PV-Syst follows this nomenclature that south facing it is calling as 0 degree. And if you want to change the azimuth, but in the northern hemisphere, it doesn't make sense to change it from this. Basically, south facing gives us the maximum output. So this remains at 0 degree, and the plane tilt angle can also be changed. And accordingly, the output, as you can see, will change. And another thing is this optimization with respect to what season you want. So whether you want to have the yearly thing or summer or winter, you can see. And accordingly, you can guess, these curves here will help you guess the tilt angle, which is the best one for your case. So suppose you want to have yearly optimization, you can see we are slightly on the lower side from the peak. So if I just decrease it maybe to around 30 degrees, then I'll get this around the peak. And that is interestingly also you can look it up. The latitude angle of Delhi is also very close to 30 degrees. So so that is always that is a sort of established analytical result, is that the year round output, if you want to maximize the year round output, then best is to put the tilt angle same as the latitude of the place. If suppose someone wants to have the maximum output in the summer months, so as you can see in the summer month, as I said, because we are in the northern hemisphere, the output will be maximum when you have the tilt angle lesser than the latitude of the place. So here, as you can see, if I go up this particular curve, green curve, so maybe maximum might be around 10 or 15 degrees, I can get the maximum output. In the winter season, again, similarly, if I increase the tilt angle, then I'll get the maximum. So maybe I'll get maximum around maybe 50 degree or something around that value. So accordingly, we can choose. So let's say I choose here the yearly irradiation yield, and I can see now that I am getting maximum around 30 degrees. So I put it there. And how much is the gain by this transposition factor due to this tilt angle? As it says here, 13% is the gain. So suppose instead of this 30 degree, if I would have placed my panel completely horizontally flat on the ground, then whatever output I would have got, now I'm with 30 degree tilt, I'm getting 13% higher output. So that is this transposition factor here. So accordingly, we can set. So let's fix it here. Yearly radiation yield maximization. Accordingly, the plane tilt should be 30 degree and the azimuth at 0 degree. And we fix this orientation. So now the orientation thing is done. And accordingly, now you see here the prompt message in this message box changes. So orientation is now in green, and that is like sorted out. Now users need is in red. And the prompt message also says here that the users needs not defined. With a standalone system, you have to define the valid or non-zero users needs. So because in the standalone system, the sizing of the entire system and simulation, is very critically dependent upon the user need values. What are the energy demand values? So this users needs need to be defined. Now again, before we go to it in the software, let's look it up in our presentation here. Some concepts related to users needs. So in the users needs, what you will find is that you'll get there will be a table of daily consumption. So how much is the energy consumption on the user's premises at the user's end, that needs to be filled up. And to complete this daily consumption table, you'll need to define the number of appliances, the power appliances which are being used, what is the power rating of these appliances, and then what is the daily operating time, for how much time these different appliances are being used. So once the definition of your energy requirements is complete, you have a balance sheet of the total daily and monthly energy consumed by your devices. And apart from this appliances which you define, there is something which is known as the standby power consumption, which is PVSys adds from its side. So as we'll go to the interface, you will see that PVSys will add around 24 watts for each day for 24 hours. That means 1 watt per hour for every hour as the standby power consumption. So that is usually because when the devices are off, or there is some standby, or a lamp type of thing which might be on, so there might be a very small power consumption like 1 watt or something which still goes. So that thing is also given there. So let's first do this one and then we'll go to the next step here. So let's go to this users needs. In the software, you can click on the users needs button and this takes you to this type of an interface. And here you can define the total consumption for around the year. So as you can see here, there are some appliances which are named here depending upon the typical appliances which are used in some households. So and then you can choose the number of those appliances, the power rating, and the daily use, how many hours per day. So first option like lamps, LED or fluorescent lamps. Suppose I take some numbers. Suppose I take 5 LED lamps or fluorescent lamps. And let's say now I need to define how much is the power rating of watt of each lamp in wattage. So suppose I define this is each of these are LED lamps and just let's say 7 watts per lamp. And for how many hours it is operational. So suppose I put 5 hours per day. So accordingly, the daily energy demand comes up here. Same way the TV, PC or mobile. Suppose I take 2 of these devices and the average power consumption, let's say I define as 50 watts, and the average daily usage, suppose another 5 hours I define here. So accordingly this calculates. Then like that you can choose. So there are some other domestic appliances. There is a fridge or a deep freeze, dish and cloth washer, and any other uses you can define. So suppose I define few more things. Suppose I take one fridge here, and so for fridge by default it will show us 24 hours every day because that's how the fridges are operated. And this, suppose I defined some 200 watt this year, sorry, is in kilowatt hour per day. So how much energy consumption it is there. So suppose it's a 200 wattage fridge and on for 24 hours. So 4800 watt hour, that means around 4.8 units. So suppose I put it as 5 units per day. So accordingly it takes it up. And then so that more or less is there, and accordingly there can be other appliances also, and all you can choose and define them here. And finally there is this as I mentioned in the presentation, that there is this standby consumer. So if there is the standby mode, the appliances will consume some little power, so maybe 1 watt in the standby mode, so accordingly 24 watt hour for that. So it adds up total here, and you get the total daily energy. So roughly around 5.7 units per day, or 171 units in a month. So this is what we got as the monthly energy consumption here. And also you can see here that this consumption definition can be an yearly thing. So the yearly is chosen here. So when you have yearly, that means this consumption, what we have pattern, what we have defined here is for the entire year, the same pattern will be there. But if you want, you can define by different seasons or months also. So someone can choose different seasons. So accordingly, you can define different values for different seasons. So let's say this value is for summer season, then winter season will have different, autumn, spring can have different values. Or even there is an option of having the monthly consumption. So you can define for each month different consumption patterns, because and that's a very good feature, because as you understand, in the winter and the summer months, different types of appliances might be used and their operating time and also will change. Like I have not defined here the ACs and fans and coolers, so which might be used in the summer season, whereas in the winter season you might be using the heaters or blowers or those things. So accordingly, you can define a seasonal load pattern or a monthly load pattern also. But let's keep it simple right now. Here I'm just defining the yearly thing. And also you can, there is this another interface here, you can see, you can define it as the weekend or the weekly use. So you can also define if you want to say have different usage pattern on the weekend and the weekdays. So you can choose this option and you can say that this particular pattern is applicable only for, let's say, 5 days in a week or whatever number of days, you can define it accordingly. So let's keep it as the default, as the a simple one. No, so entire year the same pattern, and for all the 7 days in the year. So accordingly, this total daily energy and monthly energy has been calculated. So this is the user's needs, and then there are some advanced options also available in this. So this is what is the basic option for defining the user's needs. But then there are different advanced options which also need to be taken up. And this advanced option basically refers to the time of use, because as you can see here we have only defined the appliances which are being used, but when are they being used is also important, because as we understand, the solar PV or the solar energy, solar radiation is only available in the daytime. And if you are consuming, but the energy consumption can be across the day, any time of the day in the 24 hours. So accordingly, whether the energy consumption is during the sunshine hours or the non-sunshine hours, accordingly the entire calculation will change. The sizing of the PV system and the sizing of the battery system, all things will need to be accordingly adjusted. So that's why you see here it says that you need to specify the hours. So there is this other tab here, as you can see, just adjacent to consumption, you have hourly distribution. So when you click on this hourly distribution, you see that there is this option of choosing the hourly consumption pattern for all the devices which you have defined. So we have defined here only 3 devices: lamps, TV, PC, mobile, and the fridge and deep freeze. So for fridge, basically by default, it takes all 24 hours. Whereas for these other two appliances which we have taken, we can define what will be the number of hours when we are using those devices. So as you can see here, we have mentioned here 5 hours per day for each of these. So now we have this option of selecting what time of the day, which 5 hours are we talking about. So let's say like you have this one. First, let's take lamps, LED or fluorescent, and this one here. So as you can see, there is this dial which is mentioned given here, the circular thing. So it starts from 0 hours, midnight, then 3 a.m., 6 a.m., 9 a.m., 12 noon, 3 p.m., 6 p.m. and 9 p.m. and again back to 0 hours. So the entire day, it tells this clock or this dial is divided into 24 sections. And there is one outer and one inner, two different dials are there. So it is for each half an hour. So you can define the slots for each half an hour. So suppose what I say here is that let's say I choose that my lamps will be on from 6 p.m. till 11 p.m. 5 hours. So accordingly I can choose here. So you can accordingly select whatever are the timings when your particular device is on. So accordingly. So as you can see, each slot is half an hour. So this is now 6 to 8. Now if I click this corresponds to 8 to 8:30, then 8:30 to 9. Accordingly 9 to 9:30, 9:30 to 10, 10 to 10:30, and 10:30 to 11. So these 10 blocks which are filled up, this makes up from 6 p.m. to 11 p.m. And same way we have for this the for the TV, PC or mobile, we have again taken another 5 hours per day. So here also again we can choose for this accordingly. So suppose I take it as let's say 3 hours during the daytime, and let's say I define it from 10 a.m. to 1 p.m. suppose I define. So this is 9 a.m. Next one is 10. So starting from 10 to 10:30, then 10:30 to 1, then sorry, 10:30 to 11, 11 to 11:30, 11:30 to 12, 12 to 12:30, and 12:30 to 1. So 3 hours here, and any 2 hours in the evening slot, suppose from 7 to 9 p.m. So 7 to 7:30, then 7:30 to 8, 8 to 8:30, and 8:30 to 9. So this is what I have defined here as my device, what are the different devices and their usage times. So accordingly, as you can see here in the bottom right, there is this graph which shows you the load pattern. So what is the load curve for your appliance specification? The hourly consumption in watt, and across the day, how it is varying, that has been plotted here. And for this present consumption, this seems okay for these devices. So I can select it OK. And now, as you can see, everything is in green. All these are OK, and the entire thing has been defined. So that is how we can define the user's needs in the simple way. But then there are advanced ways also available. So this is what we discussed just now. And suppose if you want to have some other way of defining, so there is this another option also. Suppose I want to give a more complicated load profile, not this simple one which I have specified here. So there is another option which is known as the users need other profile. In this other profile, what is there is that there are different ways in which you can define the your consumption. You can load a model, or you can have fixed constant consumption. You can have monthly values, daily values, household consumers, or you can most flexible one, or the one which provides maximum flexibility, is that you can load the load values from a CSV or hourly or daily file. So basically a CSV comma separated values file which you can create in a spreadsheet program like Microsoft Excel, and that you can load here in the software as well. And the template for that is available in PVSys. When you download PVSys, there is this file parameters hourly parameter template .csv which is available, and that will be the file location when you download the software. Usually this whatever is the PVSys version 7.x, that's why it is mentioned, it is usually stored in the C drive in the program files. So in that PVSys folder you can go, and you can go to this path name, the data ro PVSys 7.0 data and templates, and in that you will find this template file, the params hourly parameter template, and that parameter file will this template file will have this type of a structure. So there will be 8,760 rows for each hour across the year, 365 into 24. So each row contains the power demand of 1 hour. Total 8760 hours for the entire year are defined, and the format of each row entry is in this format. So the date, DDMMYY format, and then the timing, the hour in hour and minute format, and then what is the power consumption in that hour. So like here, a section of that file is shown here, like, so on 31st December 1990, from 23 hours, that means from 11 p.m. to midnight, the power consumption was 80 watts. Before that hour, it was 120, then 150, like that. So that type of thing is also available, and I mean, it might not be very useful for household consumption and all, for household use. But if you have an industrial consumer or having more complicated load profile, then that type of option might be used. So in other profile, you can accordingly, as I said, you can choose your load values from a CSV or hourly file, and you can choose the CSV file, and you can load it here. So that option is available, but right now we'll not go with that option. We'll just go with our default one. So I'll just correct this for our basic simple one, and so that we can move ahead with the simulation. So the same thing which I defined earlier. So this was what we had decided upon, and we'll go ahead with this one only. So this is the user's needs, and now we have defined the user needs. So as you can see, the user's needs is also in green. And now the message here in the message box says, please define the system. So next step is defining the system. So again, let's look at some basic ideas related to this. So once you have finished defining the system orientation and your user needs, the system tab will turn red, which means that you can click on it to define your electrical system. So here you need to define your details of these things in the system tab. You need to define the characteristics of the battery pack, characteristics of the photovoltaic field, and characteristics of the charge and discharge regulator. And if you want, you can add optional generator system via the backup tab. So these all options are there. Now let's understand few concepts here before we go to modeling this. So average daily needs comes from the user's need defined earlier. So the user's needs, what you have defined, that will give the average daily needs which will be required for sizing the system. Then another one here, you'll see there is one tab for PLOL, which is actually the LOLP. As in electrical energy, we define in electrical engineering terms, the loss of load probability. So this value is the probability that the user's needs cannot be supplied, or the time fraction when the battery is disconnected due to the low charge regulator security. So that's a standard practice in power systems, as people from electrical engineering background will be aware that the loss of load probability defines that what is the reliability of the system you want, and for how many, what fraction of time you can afford to go without the power demand being met. So accordingly, that LOLP fraction can be defined. Then in this software, how they calculate the LOLP is that they use a simplified and fast yearly simulation. The program splits the monthly meteor values into a realistic random sequence of 365 days, each day being divided into 3 periods: morning, that is the day with solar gains. Morning is the time when there is no significant solar gain. Then second is the day when the solar gain is there, and then the evening when again the solar gain is not there. And then it performs a day by day balance and reports the daily system state in order to accumulate a realistic PLOL yearly value. So basically, you can specify what is the loss of load probability you want to go for, and it will do the simulation and check at the back end, splitting the entire year each day into 3 periods, and seeing that depending upon what size of battery and PV you're taking, whether you are able to satisfy the demand in all these different sections of the day or not. And accordingly, it does that particular simulation. So this process is repeated with different PV array sizes in order to find the exact PV size matching the required PLOL. So it will do that optimization at the back end and give you the optimal size of the PV, which matches your loss of load probability. Then another thing which you will need to define in the system is the system autonomy. So again, this you might be aware is a standard term, PV system autonomy, which basically defines that if the sun is not available continuously for X number of days, then also you are able to meet your energy demand. So as it says here that this is needed. Why? Because you have to anticipate for periods with cloudy weather and you have to plan a reserve energy capacity stored in the batteries. So this reserve capacity is referred to as the PV system autonomy, and which means a period of time that the system is not dependent on energy generated by PV modules, and it is rated in days. So how many days continuously if you have cloudy weather and still you want to have your sufficient PV output, that thing needs to be defined here in terms of autonomy. So usually 2 days or 3 days might be good enough for a residential consumer, whereas if you have more critical applications like a telecommunication tower or some small scale industry or some other more critical application, then probably especially for telecommunication towers and all, this is defined 5 days plus. So in 5, 7, 8 or 10 days, again depending upon a lot of things, what location you are having, where you are installing the system, what type of weather pattern is there, how critical is your application, and what is the economics of it, how much one is willing to pay for it. So accordingly, the system autonomy needs to be defined. So as it says here, the autonomy of the system depends on the type of loads. For critical loads such as telecommunications components, the autonomy can be 10 days and more, whereas for residential use, it is usually 5 days or less. So this is important, and what will be the trade-off is mentioned here. When defining a very large autonomy, the global system optimization process will choose the minimum PV size which just meets the required LOLP. This may lead to a very low average state of charge value over large periods of the year, which is quite damaging for the battery. So that is one catch here, that if you define a very large autonomy, let's say 10 days or something like that, 15 days, that means your battery will be really oversized, that it can supply that particular time of that entire duration. And now what the optimization will do, the optimization of PV system, what it will do is that it will choose the minimum PV size which just satisfies this particular LOLP. So what will happen is that because the PV size is very low, so usually the average state of charge of the battery will also be very low for large periods across the year. And this might be damaging for the life of the battery. So that is one thing which is a critical thing in this respect. So in these cases, the actual PV array sizing should be slightly increased with respect to the PV system proposal. So that is like one insight which you can use for practically sizing it, is that when you choose a very large system autonomy, whatever is the PV size your PV system is suggesting based on its internal calculation, you can oversize or have a larger PV array so that you can minimize this effect of the damage to the battery life due to the low state of charge. So that is there. Then another thing is the battery capacity. So battery capacity calculation takes the minimum state of charge, disconnecting threshold, and the battery energy efficiency into account. All these are accounted for. It also has to apply capacity correction as this mode of use. That means the system autonomy mode of use, when you are not having any PV input and for long periods it is just cloudy weather and you are generating, you're supplying the load from your battery itself. So in that thing, usually the discharge is a very slow discharge, for let's say for 10 days or so, you are discharging the battery slowly. So it's a slow discharge rate, and therefore it corresponds to C100 capacity definition. That is with discharge in about 100 hours. Whereas the nominal capacity of the batteries in the PVSys database is defined as the standard value as the C10 value. That means for 10 hours of discharge. And so there again has to be a correction factor, which again it takes care of accordingly. The software will take care of it. Is that the C100 by C10 ratio is usually in the order of 120% to 130%. So usually there will be oversizing of the battery due to that slow discharge rate. Then there are other things also which you need to choose upon. We'll come to this in the interface, but let's first go through the concepts. So another thing which you need to choose upon is the battery voltage. So at what voltage will your battery system operate? So in a standalone PV system with direct coupling to the user without inverter, the battery voltage determines the distribution voltage. So that's quite obvious because you don't have an inverter in between. So whatever is the battery voltage, that is what will be the distribution voltage in your DC microgrid type of thing. So this choice should be made according to system and or appliance power, as well as the extension of the planned distribution grid to minimize the ohmic wiring losses. So accordingly, a judicious choice of battery voltage should be made so that whatever are the appliances which are still there in the system, and also if there is an extension which is planned for the distribution grid, because if we operate at a very low voltage, then we understand that with larger power requirement, the current drawn will be higher, and that will lead to much larger ohmic losses. So that's why this choice should be made at the early planning stage of an installation, since the existing appliance voltage usually cannot be changed and voltage translators will be expensive and not 100% efficient. So this needs to be a judicious choice. And depending upon how much load you foresee in the system and in your particular DC microgrid type of thing, because it's a standalone system we are talking about. So depending upon that particular load which is there and how much expansion you foresee, accordingly, you need to choose upon the voltage level, and the most common voltage levels chosen are 12 volts, 24 volts, or 48 volts. And here are some just some thumb rules or guidelines for making the appropriate choice. So the 12-volt systems usually are the little systems for lighting and TV. The SHS type, small household system, solar home system, which is used only for small applications like lighting and TV, etc. And here the appliance maximum power of any one appliance is less than 300 watt, whereas the corresponding current accordingly will be up to 25 amperes, and the inverter should be less. If you have an inverter, in this case, should be less than 1 kilowatt. So in that case, 12 volt would be a judicious choice. And the next voltage level is 24 volts, which is used for a medium sized system. So you can relate it with the discussion we had in the beginning of the presentation. So if you have a medium sized standalone PV system, 24 volts might be a better choice. And this corresponds to a household with fridge and little appliances or wiring extension to more than 10 meters. Here the appliance maximum power should be less than 1000 watts. So accordingly, the corresponding maximum current will be up to 42 amperes. And the inverter should be, if it is there, then it should be less than 5 kilowatt. And same way, the 48 volts is used for special industrial or agricultural use. And here industrial, as we all obviously understand, is referring to the small scale industry. So if you have small scale industry or agricultural use, then this 48 volt might be useful. And here the appliance maximum power is less than 3 kilowatts. The corresponding current accordingly will be up to 62 amperes, and the inverter rating will be less than 15 kilowatts. So these are the typical voltage levels, and accordingly the power rating up to which the appliance maximum power can go, accordingly the voltage level and all can be decided. And if you have higher power requirement more than this, then that requires either high DC voltage or AC feeding through inverter. So those things accordingly we can choose upon. So and then there is a so accordingly the battery voltage choice can be made. And there is one more thing which we will see here is the pre-sizing tool, which is like again a tool which has been given by the PVSys software for helping you decide upon the suggested battery capacity and the suggested PV power. So okay, let's first look it up to this level, and then we'll go to that pre-sizing tool. So let's go to the system interface here. And when you click on the system interface, this is what you get here. As you can see, this type of dialog box comes up. Now here and if you look at the top left corner here, it says average daily needs 5.7 kilowatt hour per day. So as you can recall, this is coming from the user's needs. Just to remind you, if you go to the user's needs, what values we gave here, this was 5.699 kilowatt hour per day. And that same thing, it is picking up here. So in the system, the average daily need is coming from the user needs which you have defined. So 5.7 kilowatt hours per day. Then enter accepted PLOL or the loss of load probability. By default, the software takes a value of 5%. If you want to change, you can always change this one. Enter requested autonomy. So this all we have discussed, right? So the loss of load probability, the fraction of the time in the year across the year when you can afford to have the battery not being able to supply the load. So 5% is what is the default which comes with the software. You can change it if needed. Enter requested autonomy in the number of days. So that means 4 here is given as the default. That means for 4 continuous days, if there is no PV generation, then also your battery will be sufficiently sized to ride through that cloudy weather and have your output to your appliances. And now again, depending upon the criticality of your loads and the location where you are located and how much you can afford to pay, Accordingly, you can change this one. Suppose, let's say I decrease this autonomy to 3 days or 2 days. So you see here the numbers are changing. The suggested capacity and the PV power, they changed. Suppose, like, I'll just show you, if you the initial guess, or the you can say the default value by the software was 4 days. So with 4 days system autonomy, the suggested battery capacity is 1117 ampere hours, and suggested PV power is 1314 watt peak. Okay, 1.3 kilowatt peak. And suppose if I decrease it to 2 days system autonomy, then you can see here that the suggested PV power slightly it increased to 1350 watt peak, whereas the suggested battery capacity dropped to half, 559 ampere hour. So that's quite obvious also, because how much system autonomy you require, that will have a direct impact on the battery capacity, because it basically means how much storage you need for power. So let's take some value. Suppose I take 3 days here. So as you can see here, suggested capacity is 838 ampere hours, and accordingly the P power is calculated. The battery voltage, again, it's chosen by default as 24 volts. Now this choice again is good for a medium-sized home having the fridge and TV and all those appliances. So this is a judicious choice as per the discussion we had. This we can, and the typical values are either 12 volt, 24 volts, or 48 volts. But as per the discussion we had on battery voltage, and also depending upon the appliances which we have chosen here, 24 volts seems to be a good choice here. So we have got this one here. Now, as you can see here, there is this detailed pre-sizing also. So this is some preliminary pre-sizing, and you can go to this detailed pre-sizing also. And in this detailed pre-sizing, there are several other things which you can play along with. So, the required loss of load probability, the battery capacity, battery voltage, the minimum state of charge. So minimum state of charge by default, it takes 20%. You can increase or decrease it also. Then PV array efficiency, which is like the performance ratio, similar to performance ratio. It is defined as 80%. So you can, if you play along with these critical parameters like the minimum SOC and the PV array efficiency, or the performance ratio, accordingly the values will change. So this is okay. Let's just leave it on those default things. Now here you can see, so we did some pre-sizing and we got some particular values, 838 ampere hours and 1329 watt peak. Now there are different things here. You can size your storage, your PV array, your backup if you want, and the overall. This is a simplified sketch of the system. Also, it is available. So let's go for this one by one. So before we go ahead, let's just look up some things here. So the pre-sizing we have done already. Now there are few things which we need to decide upon before we go ahead. So let's go through this aspects also before we go to the system executing the simulation. So pre-sizing we have done. So with this tool, you can define a maximum surface or power that you want to install. When a value is defined in one of the two boxes, the software will make a wiring suggestion via the PV array design tool. So you can, in your detailed pre-sizing also, if you want, you can make a change. Suppose if you want to change your battery capacity, or your, if you want to show with respect to the loss of load probability or with respect to the PV distribution, accordingly you can make this one. And here, so this is okay. Let's leave this as okay. I think this is pretty good. Now let's look at this, the options available for batteries. So, so the battery set, you can sort the batteries by voltage, by capacity, or by manufacturer. So here, let's say it is giving by default as by voltage. Now there are different, you can see there are different manufacturers whose batteries are given in the database. Let's choose all manufacturers for ease of this thing. And there are different technology options also available. I mean, only two options at present, either lithium-ion batteries or lead acid batteries. So if one wants to go for a particular technology, battery technology, that can also be chosen. Let's put it here. This also has all technologies and all manufacturers. And you can see here the different options are coming up here. And accordingly, you can make a choice for this. We have chosen a 24 volt system and 838 ampere hours. So accordingly, we can make a choice for the, so battery voltage should be typically less than 24 volts now. So suppose I go for a 13.2 volts thing. And here accordingly it will do the calculation how many modules in series and how many modules in parallel will be needed. Now again, this is the same, the basic calculation all of you might be able to recall, that how many number of modules you have in series decides the voltage level, right? And how many modules you have in parallel will accordingly decide how much will be the current output. So based on what we had, this is doing some calculation. But as you can see, modules in series is highlighted in red. Why? Because if you put two modules in series, this goes up to around 26.4 volts, which is, accordingly, you can see your battery voltage has been updated here. But that is not really a standard voltage. So, that's not really very convenient maybe. So let's choose something lower. Suppose I choose this 12 volt battery and having much larger ampere hour rating. Let's say you can go through this database. You can see there are different combinations available in terms of the voltage and the ampere hour ratings. So suppose I want to go for 12 volt only, but higher ampere hour ratings, 848 or something was the value. So suppose I take this one. So now you can see this seems to be relatively okay, but still this is showing in batteries in series is showing in red. Let's see if I can get, because usually, the for charging, it's better if the battery voltage is slightly lesser than whatever is the rated voltage. So here what we see is that there are 8 volt batteries also available. Suppose I choose this one. Let's see. Not really helping it out, but okay. So let's go with this 12 volt thing only. And suppose I take this, what we had taken earlier. So suppose I take one of these batteries here, like that. So I got the, this is sort of okay, and I got the batteries, this thing, the choice of the battery. Now it says here, please choose the PV array. So I need to go to the PV array block here, and here again there is this pre-sizing help. So it is taking this value, how much, what type of PV array you require, that you can mention either by by the available area or by the needed power rating. So this is taking this 1329 watt peak is coming directly from here, the initial pre-sizing. So let's go with this option only, because that pre-sizing has been done taking into account our loss of load probability, autonomy, and the user needs. So I selected this one, and same way here you can select the PV module. The whatever modules are available now, those databases here, you can choose a particular manufacturer if you want. Some different manufacturers, their database, and no, the PV modules available from those different manufacturers are available here. Suppose I just to take it as all manufacturers. So it will give the entire listing here, and the power rating and the voltage rating, it is sorted with respect to that. So suppose I take this 24 volt 50 watt peak panels. So now I've got this one here, and accordingly you can see how many modules in series and how many number of strings. The same logic goes here also. So the modules in series will be determined according as per the voltage level, and the number of strings will be depending upon how much will be the current output needed. Accordingly it will be calculated. And now it says here, please choose the controller model or the operating model for a universal controller. So you need to choose the controller also here. Now a few comments about the controller. Let's quickly look at it before we go into that. So the best choice, usually people go for the universal controller. So so this thing here is important, and something interesting is given here is that during the early stage of a standalone system study, the main issues are the global system sizing, that is determination of the battery pack, the PV array power as function of the user's needs, and the meteorological conditions. After the quick pre-sizing evaluation, the results, which is the LOLP, unused energy, must be assessed with a detailed hourly simulation. The exact regulatory strategy does not matter. To get rid of the control constraints, PVSys introduces a general purpose generic universal controller for the three different strategies: direct coupling, MPPT converter, or DC-DC converter. So this is something interesting. Like the PVSys is giving this universal controller, which is like a generic controller which can deal with any of these strategy, whether you are having a direct coupling, like in the case of your small standalone PV system, or you have an MPPT converter based system like your medium sized system, or a separate DC-DC converter like what we discussed in the high power standalone PV systems. So across these different configurations, this universal controller has been given by PVSys. And so one can choose this one, and during the sizing process, that means the specification of the battery pack and the PV array, these special devices will adapt their parameters to the system in order to always stay compatible with the normal behavior without control losses during the early simulation. So there are different parameters. If you want, you can change those also. That those options are available with the universal controller. You can change the hidden parameters, the temperature correction, the maximum charging, load, and backup currents. There are a lot of parameters which you can change, but if you want a particular to keep a specific configuration for further use, you can always save that also as the universal controller. So those options are available. So let's go to this universal controller. You can see here, as you can see, universal controller is ticked by default, and it's a generic controller which we are talking about, not a particular manufacturer one. And you can choose if you want what type of operational mode you want to operate it. Accordingly, you can choose the operating mode. So that the same universal controller can be will be adjusted as per the operating mode. Now in this case, what we are talking about is like a medium-sized system with 24-volt battery usage, and the power rating is also around 1.3 kilowatt peak. So I mean, it can due to the low power rating, 1.3 kilowatt peak, it classifies in that particular range, also up to 2 kilowatt peak. What we said was the medium size systems, and also with respect to the voltage rating also. So let's, as we discussed, for the medium size thing, MPPT converter based system operating mode would be better. So accordingly, it has once I selected the MPPT converter mode, accordingly it gave us one particular universal controller with respect to the the given parameters, the voltage rating and the power rating and all. And if you want to change some parameters, that was what I was mentioning there in the in the presentation, is that there are a lot of parameters of this which you can change. So the maximum charging current, maximum discharging current, maximum backup current, all those different things are there which can be played along with. But if one has the data sheet of a particular controller and they have those values, accordingly they can play along with these values. There are a lot of parameters which are available for manipulation here. So accordingly it can be done. Or in case you don't have a particular data sheet, or the from specific things, details of the particular product, then you can just go with this default what is given by the PVSys. In case you have it, accordingly you can modify those things from this dialog box also. So those options are there. And so now this completes the sizing thing, because we have done the storage, the choice of the battery, choice of the PV array, choice of the controller. And if someone wants to add a backup generator set, that also is available. That option is there, but let's not go into that right now here. And let's do it. OK. And now, as you can see, everything is green. The system is also green. We have defined the system. And now you can see here, it says ready for simulation in the green. And accordingly, once you have defined all these things, now you can execute the simulation, and you can see the results. So let's do the simulation now. Once we have done this thing, now we can run the simulation here. So you can see this green button, run the simulation, and you can run it here. And that's how the simulation runs, and it shows you the majority of the outputs. There's some interesting insights and all you get from here. So this is what the output result dialog box looks like by default. And here there are 4 graphs which are given by default. There are a lot of other details here in these tabs on the right hand side. We'll go to these one by one. So let's start from top here. So to our top left, you can see the specification of your location and the type of system is given. What PV modules we chose, what was the battery we chose, the ratings and all, the nominal power, the MPP voltage, MPP current, battery voltage, total capacity, all is given here. And this is the main results of the simulation you can see on the top right side. How much is the total system production? So this system, 1.6 kilowatt peak system located in Delhi, and the entire production across the year is 2,974, around 3,000 units per year. The specific production, that means the kilowatt hour units, output kilowatt hour per kilowatt peak per year, is also mentioned here. Performance ratio of the entire PV system, it's pretty low here. You can see it's around only 59%. And the normalized production, the array losses, the system losses, all these things have been calculated. Here you can see a few graphs, and this one you can see the daily input output diagram. Here you can see there is this, the input output would have gone along this diagonal line basically, because as you can see in this graph, the effective energy at the output of the array is on the y-axis, and the global incident radiation in the collector plane is on the x-axis. So theoretically speaking, the output should have gone along this diagonal line, these dots along the diagonal line. But you can see here there's a plateau coming here, and that plateau is coming due to the battery size. So we have sized the battery appropriately as per our users' needs. So there is some excess energy which we are not capturing, which could have been there if we had a larger battery size. But due to that battery size limitation, this is a plateau which is coming here. Then here you have the performance ratio on the right hand side. So this performance ratio is pretty low across the year. You can see some months it is going higher also, but overall the value is pretty low, around 59%. Then bottom here, array power distribution, the effective power at the output of the array, and the effective energy at the output of the array. So energy versus power, it is showing here. And then you have the array temperature versus the effective irradiation. So how much is the array temperature and how it is varying across the irradiation. So you can see, the variation is from right from up to close to 0 degree, then in the winter months and all, and goes up to 40 degree Celsius even at low irradiation. And as the irradiation goes high, when you have irradiation around 1000 watt per meter square, and the peak is like around 1000 to 1100 watt per meter square is the annual peak of irradiation. And in that particular condition, the temperature or the array temperature is going as high as up to 60 to 80 degree, around 60 to roughly in that range, 60 to 80 degrees Celsius. So that type of variation of temperature is also given for that appropriate, we can take appropriate corrective measures if we find that the temperature is going very high, and accordingly, because this will have an impact on the output of the system also. So these few graphs are there. The detailed report you can get from here, right hand side, you can get this detailed report. When you click this, you'll see that this type of report is generated by PVSys, which is the default report. And you can, if you want, you can save this document as PDF. It will give you output as the PDF, and you can choose the pages here. And let's zoom in a little bit because this is not really visible. So you see this second page is just the sort of cover page only, some primary things are given. Then on the third page, you have the details of the PV array characteristics, which you have chosen, the array losses, the battery management control, and all the battery details, and accordingly its management and all is also given here. On the fourth page, you have the user needs, which we defined in the user needs section. Fifth page here, you have the main results. So you can see what are the different, where the output is going, the normalized production. So there's a lot of unused energy here. You see this indigo colored thing, the dark blue in this graph, that is the unused energy. That is what is showing as the saturation in the output graph, because that is not being used due to the battery capacity. And then there are different other things. So YF, this maroon one, is the energy supplied to the user. And YR is the entire thing, the entire radiation energy which is available. So there's a lot of unused energy which is going. Then green one is the system losses and battery charging losses, and purple one is the collection losses or the PV array losses. So overall, this losses, losses are pretty low that way, but there is a lot of unused energy, and that's why the performance ratio is coming out low here. So how much energy you are supplying to the user divided by the whatever is the total incident energy. So the performance ratio is pretty low here, around 59% that way. So this is there. And then the energy balance across the year is also given in terms of, how much is incident and what you are capturing. And this also shows here the loss diagram on the next page. You can see the Sankey diagram type of thing is given. How much is the total energy incident from the global horizontal radiation, then the different losses, the losses in the collection of the solar energy, the array losses, the effective energy at the output of the array, then battery storage, and finally how much you're getting. So those things are given here, and this 7th page is the that same input output graph, that is also given. So all these things are there, and this report is also quite interesting and useful and can be used. Then there are different tables which you can generate, depending upon what type of outputs you want to see. You can have custom made tables. There are some predefined graphs. A lot of information is there in terms of the different factors, parameters which you want to see, how you want, how they compare. There are some hourly graphs in terms of the solar characteristics, how they are varying across the year and across different hours. You can also do the economic evaluation here if you specify what is the costing of your PV modules, batteries, controllers, and all. And you can choose the currency. The default is euro. You can choose Indian rupees or appropriate currency, and you can do the costing as well. And and then the loss diagram is the same, the Sankey diagram which we discussed. So all these options are there, and this completes the this simulation. And then you can, if you want, you can save the results. And this variant of your project, the same daily sample project .vc0 is the default variant, and we can save this variant, and we can close it. So now the simulation is done, the variant is ready, and VC0 is the new simulation variant. If you want to create a new variant, you can always choose a new simulation variant from here, and you can choose this one here. Sorry, this new variant you can choose, and you can create another VC1. So you can create different variants for the same location, for the same details. Or maybe you can choose different things and see if you want to change the location, what will happen. If you want to change the orientation, what will happen. If you change the user's needs or the system parameters, you can create different variants. So VC1, VC2, and so on. So like that, different variants can be created. VC0 is what we have already simulated, and the result is ready. So same way you can create different variants, VC1, 2, 3, and so on. And you can see the effect of change of these parameters on the output. So this sort of completes only the one half of standalone, and only the modeling and simulation of standalone PV systems. Grid connected, we don't have time for it, and I'll give you the slides. You can go through this. And in grid connected, the most of the steps are similar as a standalone PV system. Only few differences are there. And there are some things known as far shadings and horizon profile and all, which you can use. There are a few things which you can change from your standalone thing, but you can go through these details because we don't have time right now. But the standalone thing is what we have discussed in detail, and this is complete. So that is it from my side. Any questions are most welcome. Anyone having any questions, you can please feel free to ask. So is someone speaking? I'm not really able to hear anyone speaking.
One question is from Prof. Sony. Sir, he's asking that fridge consumes 200 watt or 500 watt.
Rating, you can check it up, and there are different options, sizes of the phrases, and the different star ratings and all are also available. That thing is, I think you can check it up with respect to what appliance you have, how much rating it is. Accordingly, you can take the number.
Another question is how to get this software.
Yeah, so the software is available on PVSYST website. You can look it up in Google. PVSYST will come up. But the thing, as I mentioned, is that the trial version is available for free for 30 days with all functionalities. But if you want to use it for a longer duration, then you will have to go for the licensed version. And we recently got a licensed version. I mean, we got the offer from PVSYST. So I mean, the pricing is also not very high. I mean, it is like 600 Swiss francs for each year of license, and also they give discount for academic usage and all. So accordingly, I mean, one can make a choice which one they want to go for.
Hello.
Yeah.
Sir, is there any open source alternative for this PVCist?
There are few things coming up, but I don't really find some good open source alternatives so far, actually. I mean, this is really good, and also it has been validated several times. So, publishing the results with this is also much more easier. For open source or new alternatives, the validation is an issue, and one probably, I don't really have any good validated alternative in my mind as of now. But one can look it up. But then again, if you want to, as a researcher, if you do some simulations and you want to publish those results, then the validation of the software becomes an issue at times.
Okay, thank you, sir.
I didn't have the time. I wanted to share one research paper which I recently published, actually, with this. Just a sample to show you a flavor of this, because most of the, this entire presentation we discussed only the modeling and simulation and how to do it. Just for your reference, because most of you here are also faculty members and researchers, so just wanted to show you the type of research which we can really can do with this. So this is one paper which we recently published on doing the approximate rooftop solar PV potential of Indian cities for high-level renewable power scenario planning. So here our focus was on developing some first cut estimates for rooftop solar PV potential. And you can go through this paper. It is available on Xavier, this Sustainable Energy Technologies and Assessments Journal. And I just wanted to show you what we did here. There are a lot of things which have gone into this thing, but one thing we did is that we simulated different building profiles and building neighborhoods. This is what the PVSys 3D model looks like. And we simulated different building neighborhoods, entire neighborhoods with different relative building sizes and separation. And we simulated these in different locations across the country. So like 5 cities we did the simulation from Thiruvananthapuram, Bangalore, and Mumbai, Kolkata, and Delhi. So in these 5 cities, these 8 different building conglomerations or building neighborhoods for different interaction between buildings. And we tried to see how the shading effect is varying, how the rooftop area usage is varying, and based on that, then we extrapolated the results. This was actually the extension work of our previous research, where we calculated the PV potential of Mumbai city from the secondary data available from public domain. And here we extrapolated that using these simulations in different cities for different building configurations, and based on that we came up with the final your PV potential for different cities. So how much is the rooftop PV potential for different Indian cities? 13 cities we took in this study, and we were able to sort of figure out what was the PV potential available. So this is just like one sample. Different studies you can conduct. You can see the effect of variation of different orientation or other parameters, or other effects in terms of the PV output using PVSys. So this is what the 3D model in the PVSys looks like. This comes as a part of the grid connected simulation. When you do the grid connected thing, you can do this 3D model definition, and accordingly the near shading and other effects you can estimate. So yeah, any other questions, anyone?
Yes, sir. One more question is, can we use the simulation results to support the proposal at industry?
Yeah, you can use it, definitely. It is very much reputed in industry, very well recognized. Anything else? Okay, so I think that's it. Thank you, everyone. We'll share the slides, and you can go through it later also. And if you have any questions, you can write to me. I put my email also in the slides. So if you have any other questions or any clarification, you can write to me also. Okay, thank you.